Alright, so while the first unit load method is uploading, I'm going to record the second unit load method right now, and this one is going to be a little bit different. Now, this is another problem that you can face on your test, and this problem is concerning the bending moment. So this question specifically asks for what is the bending moment at C. Okay. Now, if you remember in the previous example, we had to find the deflection, right? And the deflection, we did the procedure, and then we used that formula in the end to find the deflection. But how do we find the bending moment? Here we're going to have to get a little bit more sophisticated and use some tricks to our advantage. All right, so this is what we're going to do. The whole principle, we're still going to use the same principle of unit load, okay? But now, to find the bending moment at C, we're actually going to use a place where there is zero deflection. Now, let me explain this to you. So, this guy has rollies, right? So that means the force is only going to be upwards. So I'm going to replace this guy with RA. This guy I'm not even going to deal with because I'm going to set my coordinate system to go like this. Oh, and this, I didn't mention this in the last video. The coordinate system is very important. Whenever you can, your choice of coordinate system will affect your calculations, right? And you always want your calculations to be as simple as possible. So the reason why I'm choosing the coordinate system to be like this, starting from the left edge, is because I don't have to worry about this guy at all, right? Because if you think about it in the future a little bit, we're going to make a cut here, and we're going to make a cut there, right, to find the bending moments. And we don't even have to worry about this guy at all, because if I start my coordinate system over here, then I have to be worried with a force this way, I have to be worried with a force this way, and I have to be worried with a moment. Because this guy is it's like an edge, it's a cantilever, right? And in a cantilever, or like a, I don't know what it's called, but there's always three forces, up, side, and moment. But this guy is just a rolly. It's just a roly-poly, so it's just gonna have a force going upwards. That's why I'm setting my coordinate system there. Whenever you can, always make your coordinate system help you the most, okay? That's how I can explain it. And furthermore, if we look at this A right here, if we look at this rolly, we know that this guy only allows deflections side to side. It's a roller, right? It only goes side to side. It cannot go up and down. What does that mean, you might ask? Well, that means that the deflection at A is equal to 0. Deflection at A is equal to 0. Very important. Okay, so delta A equals 0. This has to be established. Since this guy is a rolly, it cannot move up and down. So delta A is equal to 0. And why do we care about that? Well, do you remember from before we had that delta is equal to integral of m bar over EI dx, right? Well, if delta is equal to 0, then this guy is equal to 0. And from that, we can find m. From that, we can find m. You see how that works? It's pretty neat. It's a very neat concept. It's very sophisticated, very nuanced. But that's what we're going to do. So, first things first. We're going to have to make our cuts. And this time, we have one single load. So we're going to have to make two cuts. One before it and one after it. But the cuts, honestly, is just the same procedure over and over again. Okay? Same procedure. All right, let's do it. So, first cut. We're going to draw our little blocks. Boing, boing, boing. And remember, we have to keep this reaction force, RA. We have to keep this reaction force. All right. So, obviously, same thing. We're going to have a shear force and a bending moment. Now, in this case, it's fairly simple because, well, you know what? I'll give you a shortcut. We don't even need to find this V, because this V is not even going to come into the equation. So let's just stick to finding m. And as always, this distance is going to be x. Okay, this distance is always going to be x because this is an arbitrary distance that we're making the cut. So let's sum the moments about this edge over here. And we're going to get, if we sum the moments, what does that give us? Well, m right here is counterclockwise. So positive m, and then RA times x equals RA times x. Easy peasy. Now let's make a cut in this second section over here. And that one is going to be a bit longer. But that's okay. Now we have to be a little careful here because we have to draw everything as is. So here we're going to have RA. Here we're going to have P, right? And then this distance, L over 2, have to be a bit careful here. And this whole distance, let me scroll down a bit. This whole distance is x. Make sure you understand that. This whole distance is x. X always starts from the beginning all the way to the place you cut. Alright? So, same procedure, we're going to have a bending moment here. And that's about it. So, now we have to, same procedure again, we're going to sum the moments about this corner over here. So, we're going to have some of the moments. M, because this is positive, it's counterclockwise, M. Now, let's be careful here. Let's look at P. Is P clockwise or counterclockwise? Well, do that thing with your hand and you'll notice that in fact it is counterclockwise. So PM plus P times what? What is this distance here? Well, this distance is just x minus L over 2, right? Just x, this whole x minus L over 2. And then don't forget we have this RA, which is going to be negative. It's going to be negative. So minus RA times x equals 0. And from this we can find that M is equal to RA times x. RA times x minus P times x minus L over 2. And you know what? One more step. I'm just gonna, let me scroll down. One more step. I'm just gonna rewrite this. I'm gonna say that M is equal to, because you see there's an x here and there's an x here, so why not just group them together? So it's just gonna be RA minus P times x plus PL over 2. Okay, so we have M in the first section is this guy. We have M in the second section is this guy. How do we put this together? Well, this all goes back to what I said in the beginning, and that is that the deflection at A is equal to 0. Okay, unit load time. We have to replace this whole thing with a unit load now, which is exactly what we're going to do. If we look back up here now, how many loads do we have? We have one load, and remember in the unit load method, we replace all the loads with just one load at the point of deflection. Okay, at the point of deflection. So you might be tempted to put this unit load here, but we're not interested in the deflection at C. We're interested in the deflection at A, right? So we are gonna actually, let's redraw this guy. We are actually gonna put this unit load at A. This is very important. And this load at C is gone. It's completely gone. Completely gone. So now we just have to make those two slices again. Okay? So first slice. Now I'm going to go a bit more quicker here because this is pretty easy. First slice here, and then this is X. We're going to have a bending moment M. And obviously M is just going to be equal to X here. If you sum the moments about this point, you're just going to get M equals X times 1. Okay? Now we make another slice over here. And now this distance right here is L over 2. If you remember from before, you can always look back. So we're going to have L over 2 here. And then this distance, again, is going to be X. And again, we are going to have a unit load. Same thing. We're going to have a bending moment. And if you can see, it's just going to be the same thing. Okay? It's literally going to be the same thing because nothing has changed. Now, here comes the fun part. Delta A equals 0. So 0 is equal to the integral of M. Ooh, sorry, I messed up a little bit. This should be M bar. Very sorry. That should be M bar. So M0 is equal to the integral of M bar over EI dx from 0 to L. And now the reason why I wanted to do this example in particular is because now we have two sections, so we actually have to split up the integral. So actually, this is going to be the integral from 0 to L over 2 of m1 bar over EI dx plus the integral from L over 2 to L of m2 times m2 bar over EI dx. Where obviously m1 and m2 are just, this would be m1 and this would be m2. This is just to represent different segments, okay? So now let me just write this out. Let me move this over. So what's m1? Let's scroll back up here. m1 was just RA times x. So this is equal to integral from 0 to L over 2 of RA times x. That's m1 bar. What is that? It's just x over EI dx plus the integral from L over 2 to L of m2 bar. What is m2? m2 is this guy right here. So let me just write that out. RA minus P times x plus PL over 2. And as you can see, this thing starts getting messy real quick. And then m2 bar is just x over EI dx. Now, this is one thing that you're going to have to take note of. So in my class, when I took this, he didn't take off points for doing the integral incorrectly. Because these integrals, they're not hard, right? This is just linear, I mean quadratic, but they are, like, you have to take care of your variables very well. So I'm just going to pull out all the constants over here. RA over EI, integral from 0 to L over 2 of x squared, right? Because this is just x squared. And now here I'm going to break this up into two integrals. One of them is going to be 1 over EI, integral from L over 2 to L of RA minus P times x squared dx plus PL over 2EI. You see I'm taking out this PL over 2 factor, L over 2 to L of x dx. Okay, let's keep trotting forward here. What's the integral of x squared? X cubed over 3. So RA over EI. Now x cubed over 3. X cubed, we're going to plug in L over 2. So it's going to be L cubed over 8 over 3. Okay, and then plus 1. Actually, I can pull this out too. RA minus P over EI. Integral of x squared, x cubed over 3. So we have to plug in the bounds. It's going to be L cubed minus L cubed over 8 over 3. Correct? And then lastly, this last one, you can see how messy it gets. Now this one is going to be x squared over 2, so it's going to be L squared minus L squared over 4 over 2. Okay? And now we just have to simplify. Jesus. Okay, L cubed over 24 EI times RA. And what I want to do here is I want to single out the RAs. I want to single out the RAs because this is what we're solving for in the end. Okay, so let me single. What's L cubed minus L cubed over 8? Well, this is 8 L cubed over 8, so it's going to be 7 L cubed over 8. So this right here is just 7 L cubed over 8. Okay, so this is going to be plus 7 L cubed over 24 EI RA minus P7 PL cubed over 24 EI. And then lastly, this guy, well, what's L squared minus L squared over 4? 4L squared, this is 3L squared over 4. So plus 3L cubed P over 4 is going to be 16 EI. Okay, I probably messed up somewhere, but you get the general idea. So now I'm going to combine like terms. You can see that we did the calculation at least somewhat correct because these things, these variables, they're all the same, right? We have L cubed EI, L cubed EI, L cubed EI, L cubed EI. Correct? Right. So I'm going to factor out RA, and we're going to have 8L cubed over 24 EI is the same thing as L cubed over 8 EI. And then here we're going to have minus P times 4. Oh geez, this is an ugly denominator. Super ugly. Can I simplify this at all? Well, whatever. Dot dot dot. And from here we solve for RA. From here we solve for RA. And let me just check the solution. Okay, the solution says RA equals 5/16 P. So I'm assuming I did everything correctly. Now, we did all this work just to find RA. And what does that give us? Let's scroll all the way back up here. So here we found that RA equals 5/16 P. And you know what? We're already done. Why are we already done? Because now we just have to take the moments about point C. So this is what we do. We just make the same cut that we usually make, but we don't do this cut at an arbitrary location now. We make this cut exactly at point X. Exactly at point X. So if we make this cut at X, we're going to have something like this. Exactly at point C. Very important. We're going to make this cut at point C. So this distance is exactly L over 2, right? And this now is RA. But before, RA was a variable. We didn't know what RA was. But now we know what RA is. It's just 5/16 P. So the bending moment at point C over here is nothing more than 5/16 P times L over 2. Or if you want to write it out, 5PL over 32. That's your answer, champ.